Now with that, let me tell you a little bit about the Science Gateways Community Institute, who brings you this webinar. We are an organization that has 3 areas of support, and our first area is offering support for building and running gateways. And that includes hands-on development support, also advice from consultants who specialize in various aspects about gateways, such as cybersecurity or usability or technology choices or sustainability. And we also have a catalog of gateways and software where you can look for products that might be something you'd want to build into your gateway, or you can promote your own gateway there, which has the advantage of both spreading the word to people who might want to use it, or also people who might want to kind of repurpose the same approach for their own gateway. Our second area of support is in education and training. We offer several things run by my area, the community engagement area, which includes this webinar series, which is monthly, and then we also have boot camps that are offered by our incubator, which is taught by the consultants who work on a project-by-project basis as well, and that's a week-long intensive program. If you notice on the previous slide, the applications for the upcoming one that will be in May are due in March. We also have a bunch of student-focused programs that are run by our workforce development area that includes internship programs. So we're always looking for people who have gateways that would like to have interns working on it during the summer, and also a coding institute for students to attend for 4 weeks during the summer, as well as a hackathon that will be at PERC this upcoming year. This will be the second one. Our annual conference, also run by the community engagement area, will be in September, late September, in San Diego this year, and that is open to anyone, and we'll be promoting our call for participation very soon. So keep that in mind. And finally, of course, our website has a lot of resources, including the recording of this webinar. And then finally, our third area of support is really by providing a network and a community. Some ways that we do that are through a partner program that lets you connect to organizations that provide services beyond what we provide. Also an affiliates program, which is software developer or software components, all of which are listed on in our catalog, but where they're willing to provide additional support for the implementation of using their software. And then our website has all sorts of information on it, including news and events, our blog, which has all sorts of useful stuff in it, and job postings. And more recently, we've created a community forum that you can sign up for. It's a Google group that will let you post questions, and also we use it as another channel for sending out information. We do have a newsletter, which presumably if you found out about this, you're on our newsletter list, but if you are here for some other reason, by all means consider joining our community forum and our newsletter list to find out about stuff. And of course, the annual conference is a great opportunity to network and connect with new members of the community. So those all fit together, and they're supported by 5 different service areas that are located at 7 universities around the country, and we hope that you'll consider working with us in other ways besides the webinar, attending the webinar series. We have one favor to ask of you, though, if you can take a minute of your time after this webinar is over, which is to give us a little bit of feedback at the end. I'll be posting this link on our chat area to make it easier for you to give us feedback, but really it just asks how useful was this for you, and then if you have suggestions of other topics for webinars, we accept them gratefully and look to do some of our upcoming programming with some of those suggestions. So with that, I'm going to stop sharing my screen and hand this off to our awesome presenter of the day, Tim Menzies, who I had the pleasure of seeing present a few years ago at a PI meeting hosted by the National Science Foundation. And today he's going to talk about research he's done about research software, essentially computational software, but it's coming out of this idea of empirically based software evaluation. So with that, Tim, I'll let you go ahead and share your screen And if you want to talk more about who you are, I know you're at in North Carolina, but you might want to let everyone else know what else there is to hear.
So, hey, thanks for the invite to talk. I've got 35 minutes of talk and I hope there'll be lots of questions. And I've been hearing a lot of, frankly, nonsense from you folks about how bad your software is. And I want to tell you that your software is literally orders of magnitude better than stuff being produced elsewhere. So there's a lot of pats on the back for this right now. These slides are available bottom right, tiny.cc Comp.Sci 19. This is coming to you from NC State, where we do a lot of software engineering. There's about 15 active IEEE fellows in software engineering right now, and I'm proud to say I'm one of the 3 IEEE fellows in this department. So we do a lot of software engineering research here. And first of all, I want to say to you that your software is great. It's great. Orders of magnitude better than what I'm seeing elsewhere. I'll show a number later on, 456. I'm going to say that the methods you're doing are producing code 400 times better code, 400 times faster, and further, you're producing stuff which has lasted decades longer than most software communities. So please pat yourself on the back. I want to say that we can learn quality agents for your stuff, ways to predict defects, but we can't use out-of-the-box standard empirical software engineering. And literally half of this work was realizing that our standard methods didn't work for your stuff, and we had to do different things. And we'll talk about the different things that we did. And I want to say that it'd be an exciting, fruitful direction for future research, effective empirical software engineering, tuning empirical software engineering methods for computational science. How's my volume? Everyone good?
Yeah, we're good.
Oh, thank you so much. Okay, so I want to thank the community for jumping in and helping with this work. We ended up being able to analyze around over 600 projects. It turns out, for reasons I'll talk to, that we can only really use about 55 of them, but but do not be alarmed about 687 down to 55. That's actually something you should be proud of, and I'll talk to you in just a moment. We started out last May with the SI2 meeting in Arlington. We had various telecons with various groups. A lot of you people were very kind to respond to our email survey. We got a lot of those email names from contacts within your group. So there's a lot of help you folks gave us. Round about September, we realized we were having problems with something called labeling, which I'll talk about. And we realized that standard methods weren't good enough, just wouldn't cut it for what you folks were doing. And so we went kind of silent until this meeting. So very happy to be at this meeting. We had to report back to you. And we're hoping to be much louder and much more present in your community after this one. This slide, don't read it too closely. Just notice that the red dots are underneath the green dots. And this is the case study we'll talk about later on in this presentation. And the red dots is what happened when we applied standard empirical software engineering to do defect prediction in your code, localizing where the bugs are, guessing where the bugs are. The red dots are using standard empirical software engineering methods. And the y-axis of this graph is something called the G value, and the higher G, the more of your bugs we're finding. And the red dots are very low values, very, very bad. And by rethinking and regrouping and tuning our methods, especially for your code, we achieved the green triangles, which are much more respectable. So instead of us riding in on a high horse and teaching you about empirical software engineering, you actually set us a very high bar, which we had to respond to. So thank you for that. And we'll come back to this chart later on. A couple of definitions. I'll just, for brevity's sake, talk about your work as Compute.Sci, computational science software. And in that area, you folks model scientific software elements. You offer integration methods between software, mashups, and you create institutes for putting things together. And I'm sure that's a very brief description of the massive amounts of work you do. Now, empirical software engineering, we seek interesting patterns in software development projects that hold across multiple projects. And by interesting, we mean insights we can learn from project 1 which we can apply to improve project 2, or even insights we can learn from project 1 to improve project 1. Now, traditionally, empirical software engineering has been a very qualitative process, and in the last 10, 15 years, with the advent of data mining, it's gone more intensely quantitative, and this report today is a quantitative data mining analysis of your work. So just a bit about me. I'm a full professor at NC State. My website is menzies.us. IEEE fellow, funding from NASA, NSF, IBM, various companies. And my lab is AI4SE.net. And there you can find many people, including who's off camera right now, Ken who did most of the work for this work, and Rahul Krishna. So those are the students we want to acknowledge as part of this work. Now, the first thing I want to tell you folks is that software is not a mysterious, software development is not a scary thing. It actually has predictable properties. You can reason about software. So just in the same way that physicists reason about stars, like stars have a life cycle. And here you can see the main sequence of stars as they go across their life cycle into larger and larger red giants. So stars have life cycles. Stars have predictable properties. Software has life cycles. Software has predictable properties. Some of you may know the Github service, which is a place to store your code online. Right now, GitHub has 28 million software development users and 57 million repositories stored there. And this is heaven for empirical software engineers. It means this is a place we can go to and we can learn patterns. We can learn patterns that hold across multiple projects. Very exciting. Now, when I say 57 million repositories, a lot of those are code that you don't really want to study. What I've got on the screen now is a set of sanity checks. You know, more than 7 developers, more than 0 requests for collaboration, more than 10 issues written by someone else, more than 1 release, more than 20 commits, longer than 1 year old. If you apply these sanity checks, then the 57 million repos in GitHub reduce to 10,000 projects, 10,000 approximately. So there is a 5,700 silly ratio. So just remember that number, 5700. So when we talk about analyzing GitHub, we don't analyze projects that aren't successful, that other people aren't using. We analyze about 10 to the 4 projects. And just remember the number 5700, which is the ratio of good projects to all projects. Now, what can be learned from that GitHub? Many, many things. Well, I talk about software analytics. I just have to cough, excuse me. Thank you. Software analytics is a workflow that distills large amounts of low volume data into high chunks of very high value data. So here are some recent press reports about what we can learn from GitHub about, you know, certain issues about gender bias and how certain aspects of the GitHub interface make it less likely that certain groups can participate, and people are racing to fix those problems. And then there's, we can learn patterns of software which destroy power usage and how to fix those. Some of you may be familiar with functional languages that are strongly typed, and now it's an empirical issue about whether they actually produce better software. And then there's things about, you know, many, many results about empirical software engineering that result from having things in GitHub. So software has gone from a black art in the 20th century to something with predictable properties in the 21st century. One example was bugs are social animals. Software bugs like to live in clumps. So a repeated result is that if you have, you know, 100,000 lines of code, most bugs live in about 20,000 lines of code. Bugs live in a small percentage of the files. So, for example, at AT&T, they reported that, you know, most of their bugs come from 20% of the files. I'm going to guess some of you out there have used the GCC compiler. The GCC compiler's got multiple modules, but most of the bug reports from GCC come from a very small number of modules. And so, for example, see the graph on the right shows the percentage of files versus bugs found. And so by the time you've looked at half the files, you found all the bugs. But if you can look at 20% of the files, you can find 70% of the bugs. And if you look at 10% of the files, you can find half the bugs. And so we often talk about a cost-benefit curve where we seek methods so you can find bugs faster. And so a standard way to improve software is if any part of the code is starting to report bugs, focus on it and things near it. So if any part, if you imagine bugs lying silent across your own code, if any bugs in any particular line start waving their hands, look for bugs in nearby lines. Okay, now that's a tiny little sliver of empirical software engineering. We've got books we can share, we have methods, we have entire conferences devoted to this. There are hundreds of PhDs a year in this area, a lot of people doing this stuff in industry. If you want to know more about empirical software engineering, myself and hundreds of other people are eager to tell you. So if you have questions along those lines, just send them down and we'll certainly help you. So let's go from general empirical software engineering now to computational science. And if there's only one thing to be gained from this seminar for you, it's just this: be very proud of your software. Be very, very proud of your software. Your software is reasonable, it's controllable, it's improvable, it's maintainable over decades. The graph shown here is the number of commits in a finite element toolkit called DEAL2 that some of you know about. And you can see that the graph at the bottom goes from 1998 to 2018, and these are the number of commits. Now, if we look at most software projects on GitHub, we see a very different pattern to what's being shown here with DEAL2. DEAL2 shows 20 years of work. Most of the software I deal with outside of the computational science community lives for 2 to 3 years. I don't have a precise number on it, but I'm going to offer you a half-life that most software dies within 2 years. In 2004, a lot of excitement about Ruby on Rails. And if you've never heard of Ruby on Rails, well, welcome to 15 years later, it just doesn't get used anymore. Swift, where's my iPhone? Here's my iPhone. We used to code in Objective-C on Swift, and then when Steve Jobs retired, that fell from favor, and now we code our iPhones with something called Swift. And Swift is very new. And so in the software world that I'm used to, code changes a lot, and code is not maintained for many, many decades. Whereas in your world, you've got lots of examples of successful code maintained over many years. Now, there's one other feature I want to point out to you about the DEAL2 graph. Can you see the increasing frequency of commits towards 2018? Like it's a bit lighter in 1998, and the frequency of commits, and a commit, of course, is an outside person suggesting an improvement and offering a patch to the code. That pattern is increasing. So not only is DEAL2 an example of decades of maintainable code, it's an example of increasingly well-maintained code. So that's fantastic right there. So there's so many other examples in your community, not just DEAL2, of code that's been maintained successfully for years by very large communities. SLAP, we can find 16,000 commits from 80 developers. Trillions, 80,000 commits from 200 developers. Elasticsearch, 40,000 commits from 1,100 developers. DEAL2, 40,000 commits from 100 active. Not only that, but the code you're producing has a longer longevity than most of the open source projects I'm dealing with. And when we talk to the people when we focused in detail on some of the computational science stuff, we found your developers, particularly the postdocs, dealing with state-of-the-art coding techniques. So if someone ever says to you that, computational science doesn't know about software engineering or isn't up to speed with the current methods, that's just not true. That's just not true. And then I when I first approached your community, I was told by other people in empirical software engineering that you folks dealt mostly in Fortran and you had no interest in improving your software methods, and that's just absolutely wrong. I'm seeing people putting Fortran in GitHub and maintaining it with modern, what I call contemporary methods. I'm seeing people using Python a lot and putting it in using modern. So I think I heard a lot of doom and gloom at SI2 last year in Arlington about how our software's bad, and I'm going to say stop it. Just stop it. There's a typo on this slide. Okay. Now, we found, thanks to your help, 678 projects that we could access online, either in GitHub or otherwise. And the first line of this slide is a typo. We didn't find 44 projects. We found 55 projects. Now, remember those sanity check rules where we said you need to be, more than 7 developers, more than 1 year old, etc. When we took your 678 projects, and we applied the sanity checks to find the projects that are actually under active development by multiple people over multiple years, we found 55 active projects. Apologies again for the 44. The number is 55 projects. Now that means that your ratio of all projects to vibrant projects is 12.5. 12.5. And remember that for standard software engineering in GitHub, we had 27 million repos, of which only 10 to the 4 actually mattered. So you folks are producing, your community is producing 456 times, and again, I think that's a typo. I think, so we're caught here. Last night, we changed the number from 44 to 55. This number, I think, is 370 times more. The ratio of good projects in your GitHub repos is 300 times larger than what's seen in normal software engineering. So that's a measure of success for your community. When you folks build software, you're more serious. You don't do so many frivolous projects. You build code that lasts longer. So please be proud. So this slide is saying when we apply the sanity checks, we found all these different projects, and that's a bit small to read. And when here's a little bit of a focus on some of them. And we're all these different computational science projects. And if you want the full list, happy to send it to you. You want the URLs, happy to send it to you. We're finishing up a report for NSF that's due February 20th, and we'll put that online and we'll send around the URL. Now, just to say the obvious, we're only reasoning about the codes we could find. Now, that's not all your code. All we could reason about was the stuff we could find in open source repositories like GitHub. So, of course, we have a sample bias in what we're reporting to you. We're only reporting a slice of your development. That said, for certain sociological reasons that I want to offer you in just a few slides, that sample is growing in size. So, yes, I'm only reporting to you the computational science code we could find in GitHub. And that's not all your codes, but that's an interesting subset of your codes, and that's a growing subset of your codes. Now, this slide is a bunch of things that I heard you folks saying at Arlington last year, and I really think you should stop saying. So I heard a lot of people almost, well, I don't want to put words in people's mouths, so I heard some people say that they almost, is resent the right word? They didn't like the idea that their research was so dependent on software. And they would say things like, we don't get paid to write software. And I'm saying, well, actually you do, and anyone who's involved in the Gateway project is actually being paid by NSF to write software. And then people said to me things like, you got to say our code's a mess. And here's that wrong number again. It should be 55, not 44. But, you know, yes, we found lots of projects, and yes, a lot of those projects have widely varying quality. But we could find 55 serious projects. And that 55 out of 687 is much larger than the 10,000 out of 27 million that we're seeing in normal software engineering. So if a community of people really builds lots of software, there's going to be some buzz on the outside, but there will be some interesting core projects. And your core projects have a higher ratio than normal conventional software engineering. Now, I was told at Arlington that we don't know much about software engineering. You folks were apologizing. As soon as I said I did research in software engineering, there was an interesting number of people that started apologizing for their code. But when we looked at what you folks did, we found that your grads and postdocs knew a lot about software engineering. And a lot of those grads and postdocs knew that NSF funds them for this amount of time and their career is this long. And a lot of those grads and postdocs knew that they could get salaries, startup packages in the order of, you know, $200,000, $300,000 a year on the West Coast if they were well versed in certain standard software packages. So they were using their postdocs not only to deliver the software you needed, but also to train themselves in the software that would position themselves for that, you know, the startup market. So I would submit that some of you folks know an awful lot about contemporary state-of-the-art software engineering methods. And this is a sociological factor that I spoke of. If perhaps the postdocs and grads know a lot about software engineering. Now also, we went and talked to some of the people at CERN about their software plans, and what they presented to us was decades-long plans on how to coordinate an international software development process around their data collection and analysis. And when I start seeing someone presenting to me a decades-long plan in software development, you know, and they were happy to totally change the development languages and all sorts of things, I'm seeing the CERN people having plans about their software that rival anything out of Microsoft. Like, how many of you have noticed the pace of change in operating systems from Microsoft, from Apple? I know the folks at CERN are producing software of just as well planned. So please don't tell me that you don't know about software engineering, because I'm finding all these examples where you do. I was told at Arlington that most of our code is bad. And I'm saying, compared to what? When you say your code's bad, what are you comparing it to? Are you comparing it to the 27 million GitHub repos that most of them are just complete rubbish? Have you realized that most of your code is built and maintained for decades, while most of software engineering contemporary projects have a half-life of about 2 years? So I think your code is relatively very good. I was told you folks don't use state-of-the-art tools. You do use state-of-the-art tools. Most of it, and I had some people complain, well, most of our software is never used. Well, get over it. That's just how it works. There are 27 million GitHub repos. There's about 10,000 that we call standard. And there's about 500 that are highly used. Lots of stars, lots of reuse. So welcome to Darwinian selection. Just because you write code doesn't mean anyone else is going to use it. But what I will say is that your ratio of interesting codes is much, much higher than standard software engineering. So please stop saying you folks don't know about software. It's just empirically wrong. All right, so let's get down to specifics. Let's talk about defect prediction from the projects.
Before you carry on, Tim, can we throw in a couple questions in there?
Absolutely.
Cool. One question came from Mona, who wanted to know why the 7+ developer criteria.
It evolved out of it's a standard in the field. Just a second.
You don't need another.
Oh yeah.
It's updated.
So there's a general concern in the software engineering field for hero programmers. And heroes, so there are projects where most of the code comes from one person. And that means that the life of that code is critically dependent on that person. And so if that person had the misfortune to fall under a bus, the whole project ends. So we have a thing of, and when we did, I think we just a moment. Can we fiddle with that? We did thresholds of 5, 6, 7, 8. It just got exponentially huger after 7.
Yes.
Yeah. So I think if you talk about thresholds of 6 versus, yeah. So it's engineering judgment standard in the field. I don't know if that's an answer.
I suspect the question came through because many gateways are built by really small teams, like 3 or fewer. So that may be where that question came from, and it would be interesting to see what would happen if you included them. But then again, I don't know what would where that would go. The second question that came in is from Patrick, who said, "Is it true that these codes you analyzed were from the computer science community? What about all the codes that physical or social scientists use on our infrastructure? Would you expect those to be of similar quality given those researchers' lack of formal CS background?"
We're seeing much more in the general community of non-CS people writing codes. So there's a doctor of philosophy at Princeton. Who knows the Pandoc toolkit? Anyone in this? So Pandoc is a toolkit for jumping between formats, like you can go Markdown to LaTeX, etc. And here's a professor of philosophy that uses Haskell to maintain Pandoc, which everyone uses. So, please do not be disparaging of our colleagues outside of CS. That said, we analyze the data that we can touch. So I think the real thing here is if you have a community that you want us to explore, a specialized community, we're happy to do that. But, you go to war with the data you can get, not the data that you want.
Okay, thanks. I'm sure that Patrick will throw in an additional follow-up if he has another question about that. So carry on with your point number 3.
Okay, so let's go to specifics. We had 678 projects. We down-selected those to 55. We then had a lot of trouble with your data. It turns out, very interesting story. We had, and it wasn't just, we had problems that turned out to be very informative. So they were really interesting problems. So because we needed a small enough set to think about very hard, we tossed the dice a couple of times, and we picked a bunch of projects that span a whole bunch of languages, and they're on the screen right now. And I think a lot of you know these projects already. Okay, so we're going to analyze these for defect prediction. We're going to see if we can look at these codes as they're released, release 1, release 2, release 3, release 4. And we're going to try and learn so if here are all the releases, where's the contrast here? If here are all the releases of the code, and the code's arriving like this, we're going to try and learn a predictor from these 2 releases, these 3 releases, to try and predict for the subsequent release. So the task is learn from prior releases so that when the code for the new release shows up, learn a predictor for where the bugs are. Okay, now you may be surprised as to what attributes we pull from GitHub. Many of you are well versed in computer science. Many of you know the debates about strongly typed languages, and you might know things about, recommendations on how deep an inheritance tree should be in an object-oriented language, and all sorts of things. You might know discussions about cohesion versus coupling. These might be words that you know. But if you're going to do a data collection exercise across, well, in this case it was 9 projects, but really the goal is to get across to all the 55 that we can analyze, plus any other specialty groups that you want to give us. You have to talk about language agnostic attributes. So these are the independent variables, and we're going to try and learn a function which, if they accept these variables, we can predict for defect prediction. Now, notice here we don't talk about classes, we don't talk about inheritance trees, we don't talk about strongly typed languages, we don't talk about, you know, the use of traits in Scala. We don't talk about a bunch of language features that a bunch of very clever people have added to some very clever languages over all time. We're talking a much more coarse-grained level. You may also notice that a lot of our attributes are not to do with the code at all. They're to do with people. Like if you look at the bottom one, developer experience on a subsystem. I mean, it's quite clear that if an inexperienced person touches the code, they can introduce more bugs. So one of the great discoveries of empirical software engineering, and this is going to sound stupid when I say it, but one of our great discoveries in the last couple of years is that people write code. And it turns out that studying people is just as informative as studying the code for working out what's going to be defective. Okay, so so those are the independent variables. Now we need to have dependent variables we're trying to predict for. Now the standard way that this stuff is done is you've got project releases R1, R2, R3, and in release I, we're going to label the comments that refer to errors. So people are entering in comments into GitHub and saying, you know, this one crashes under such and such a condition. And so we're going to have to label those. And then using something called the SCZ algorithm, that goes back and says these code changes are associated with that bug. And SCZ is pretty standard in the field. We're going to mark that code as defective, and we're going to build a predictor for that as a target. And that predictor we're going to apply to release I+1. Now it's just very bad applying the predictor back to yourself, because that's like a self-test. And then you suffer from overgeneralization. In this rig where you learn from release I and test on release I+1, you're testing on data not seen in training. And that's good practice. Now, I want to focus on one particular part of this cycle, and that is labeling the commits. So someone's made comments and said, this could be a problem right here. And we have to go through over, you know, thousands, tens of thousands, and said, this is a commit. This is a commit for that led to a bug. Now, the standard way for looking at a comment and saying that comment is associated with an error is called keywords. And so someone produces a magic list of words, and if you can see these problems in it, you increase the probability that this is associated with a bug. Now, this keyword method has the advantage that it's linear time, it can run over a large space, but what we found was that these keywords, which have proved useful in the past for software engineering applications, were actually appalling for talking about computational science projects. You folks use a different language when you describe software bugs. And we couldn't use the standard language from other software projects outside your community to predict for your bugs. So we're back to this graph again we started with. The y-axis is called the G measure. It is the harmonic mean. It's the harmonic mean of recall and 1 minus false alarm. It has the property that if this is large, you're finding most bugs with fewer false alarms. And because it's a harmonic mean, if either half of it's high, it brings down the whole thing. Now, and then across the y-axis, I hope it's big enough for you to see, you can see 9 of your software projects, your kind of projects. And the red dots are what happened when we applied the keyword thing. Now, just to remind you, the red dots is what happens when we used what we've learned from other software engineering projects to decide if this comment that you're writing actually refers to a bug. And we get rubbish results. I mean, have a look at lamps. Nothing, no G over 20%. And these are really bad. Like you want these up, you know, above 60, 70, 80%. Okay, so let's look at that process again. Okay, let's talk about labeling the comments. Now, what we did was and this is pulling out all the stops. We started using active learning. And active learning, some of you know as an educational concept. But in machine learning, active learning says there's an oracle you can ask, and you want to ask that oracle the least number of times to maximize the power of your classifier. If you've got the world's greatest obstetrics doctor, and at an incredibly high cost you bring in the world's greatest obstetrics doctor, and you keep showing that doctor healthy babies, you've wasted everyone's time. If instead you show that obstetrician your most complicated case, the one you're so confused about, the doctor can say, well, under these circumstances, this is a defective or non-defective baby. So then you go back to all your other babies you haven't looked at yet and sort them out into interesting and non-interesting according to that criteria. And then you find the most complicated case of the remaining and show it to the obstetrics doctor. So this is the active learning loop. The classifier reflects on the model built so far, and this is a text mining model, this is support vector machines, and it presents to the user, I think this commit is referring to a bug. And the user goes, no, it's not, no, it's not. So you have to fix it up. Now, in terms of most interesting, for those of you who know what a support vector machine is, we find the hyperplane that separates defective and non-defective, and then we ask, what are the examples in the middle of the hyperplane? That is to say, the ones we're most confused about. And they're the ones we label next. And what we found is that we could do better labeling of the commits. We could learn your language for what you say are bugs. And we could apply that as a predictor, as a way of saying what's bugs. Which means to say that in what I'm about to show you, we did defect prediction for computational science code, but we didn't use a trite list of words taken verbatim from old-fashioned software engineering. Instead, we used a language model that was tuned to your particular language that we see in your code, in your commits. And when we did that, we get the green dots. And you can see much higher G-scores. Now, these are PCM Solver. We only had access to 2 releases. So in PCM Solver, there's only one release, there's only one result. And the red dots are below their associated green dots. And so when looking at this, we can only find 2 examples where the red's bigger than the green. Usually, once we learnt your language and used that to classify your bugs, then we could make a bug predictor. So what we're saying here is that you folks produce very good code. It produces, and this 370 number is actually accurate. The ratio of good to silly code that you're producing is orders of magnitude higher than what we're seeing elsewhere. The code you're producing lasts decades, not years, and you should be very proud of that. We can learn quality agents, the bug predictors, for your kind of code, but we should not use out-of-the-box standard empirical software engineering methods. We have to tune the language model that you use to describe your commits. And we've done that. And so we think there is an interesting area of fruitful research called effective empirical software engineering for computational science. It will be drawn from our prior work on empirical software engineering, but it will require extensive tuning to your domain. And what we've done with this Eager funding from NSF, and we should certainly thank NSF for the funding, is that we've found a general method for doing that tuning for one particular part of this. And there should acknowledgements. We really need to thank a whole bunch of people, various individuals that were generous with their time, people from Menzies and SGCI, and people from CERN who were kind enough to give us access to their people and their ideas. So thank you for that. Questions or comments?
Yeah, there was one. It's more of a comment, but it might be something you'll want to comment on. That is from the Cheryl group. I think it's actually, I think when I saw a little clip of their video at one point when they had it on, it's a group of people in a room. So this is a bunch of people. And the comment was that of the 55 computational codes that were labeled as good, it seems like many are computational chemistry written by chemists. And they list PSI4, PCM solver, LAMPS, Pi, SCF, etc. are all chemist written.
So that's an example where folks who aren't computer scientists are producing what we would call good code. So now the grad students on those projects, I'm trying to find that list of codes. There we go. The grad students on that project know that NSF, God love them, will fund them for years, and sometimes not decades. So they're structuring their own career to take the next step after their postdoc. And if you look at numerous areas of data science, we often find people that trained in economics or in physics or in chemistry, and now they've moved over to commercial data mining applications. So it's really quite common to find folks who aren't what you call traditional computer scientists building useful code. And that's a good thing.
Yeah, that's interesting. It's particularly interesting that computational chemistry is, I know, a really thriving area of this kind of work. So it's not surprising that is coming out of that area. So far, there are not other questions popping up, but we'll give folks a minute or two if they'd like to put questions in. Oh, here came another one. Oh, two more. Here we go. Okay. Did you want to say something, though, before I give you some more questions?
Well, like I say, we go to war with the data we can find.
Uh-huh.
So we don't mean to disenfranchise anybody or say certain parts of your field are bad and other parts are good. We're just saying that this is the data we could find.
Right. And of course, it may be that certain, like GitHub is more popular for certain people or whatever too as well. So, So, okay. So here's another question from James. It says, would another interesting comparison group for the non-Compute.Sci be projects in Apache or Eclipse?
Yes. Most of the work I see in the empirical software engineering literature comes from those. But because we found the language problem in what we did here, I would be cautious of using methods verbatim from Apache on generally. I think there needs to be a commissioning period where you think very hard about the method you're applying. Apply it to a small random sample and then do manual sanity checks, for example.
Okay, and James, if you have any follow-up questions about that, you're welcome to post that here. Oh, he says, sure, need to tune for good comparison with Compute.Sci. Compute.Sci. So I guess
sure
he's
what the
he's just responding to your comment, saying you need to. Yeah, he says he was agreeing. Yes. So now another question comes from Mona again. For your GitHub numbers, does it include both public and private repositories?
By definition, no. So, dear audience, question for you: why doesn't it include private repos?
I guess that is a rhetorical question. Yes.
Yes, ma'am.
you have no access.
Yes, ma'am.
And Mona responded, because it is private.
You go to war with the data you can get, not the data that you want.
Right. All right. Another question that just came in is from Marlon. He says, based on your research, what kind of software engineering advice do you have for projects?
Listen to your postdocs. Write down the sort of stuff you'd need to get a job on a West Coast startup and learn that.
You mean the software that you would need to know, or the engineering methods?
My grad students who are working in that world tell the story that most of the companies there have a very small software suite. And so once you know your GitHub and your Travises and your Jenkins and your Cucumbers, you can jump from project to project. Instead of taking weeks to learn methods in a new company, there's stories of people walking in, sitting down, and they're productive on day one because there's a uniformity to the toolkit. Now, if you go into the Microsoft world, there's a difference. The toolkits aren't quite so open. But have you noticed Microsoft's recent movements in the last 2 years to embrace open source? Did anyone notice a while back that Microsoft, the company famous for closed source solutions, bought GitHub last year?
Oh, hey, I didn't know that.
So we're seeing more and
We
more
saw a yup.
embrace of open source methods.
Yeah, fascinating. Then we have another question or comment or question from Cheryl Group again. It says, how does the mining of commit messages work within the fork and PR model? Most bugs that might be introduced by a particular commit are found and addressed before merging into the upstream code base.
What's the problem with that? Like if you're saying that there's this intensive period where a developer works with their own code and removes the bugs, then good. The problems we have with software development are not with the manic activity one person does. The problems we're having is with if you want a predictor for code success and code failure, ask what's the effective communication between developers. James Hirschlab gave a fantastic keynote at IEEE in India 2014, and he offered a socio-technical perspective on software development. And he said, code is written by people. If two pieces of code talk to each other, and this code is developed by this person, this is developed by that person, and the people whose code talk to each other do not talk to each other, that's his greatest predictor for a bug.
Interesting. Yeah, the Cheryl Group clarified. They said, yes, just hoping for clarification on your bug prediction model. So that was the origin of that.
Well, it's for the stuff that comes back into the main branch.
Mm-hmm. Okay.
And then I know in the Microsoft world there are very long-lived branches, but branching is a whole animal, and there are people that swear by the one branch model, like Firefox, just keeps everything on main, God bless them, and has these really elaborate. This is so interesting. How much time we got? I can't tell the story, but there's all these one branch models of software development. It's really weird. Software is so interesting.
Yep. So then when we have one, I'm going to share, I just shared my screen just so people can see what our upcoming webinar is going to be. We do have one more question, and I am attempting to find again those. There we go. Got the chat now. There's a question from James. Can we compare with the internal portfolio of projects in Microsoft or another large company such as Bosch? Any comparable data on that?
Yes and no. I don't know about Bosch, but Microsoft, their empirical people are legendary for their openness. If you're willing to go to their company for the summer, they'll give you a Microsoft badge. You can work inside their firewalls. They're amazing at their openness. However, their willingness to share specifics, I mean, you can publish papers from it, but there's always this proprietary problem. So I know companies that are better than others at doing what you're asking, but in terms of being able to run over 10,000 projects, it's got to be the open source world. Did anyone hear me? Hello, we just crashed.
No, I can hear you.
I can hear you, Tim.
Oh, sorry. I was talking and I had myself muted still. Yes, I was going to say you may want to connect with James. He has a little a side comment that says Marcelo Cataldo has some data from internal development as Bosch, I think. So I'll grab that.
In Bosch, what's their particular bent on computational science? Excuse my ignorance.
Can I talk?
Yeah, go ahead.
I'm happy to talk. Yeah, really cool stuff. I'm just with asking about comparisons to Apache projects and comparisons to Eclipse and also commercial projects. I think that the general open source world is an excellent comparison, and that Compute.Sci should be, much prouder of the work that they do. And one way to really confirm that would also be able to say, hey, you're at least as good as people you think are really great, like Microsoft, like a large company. So if you want data on, okay, so a portfolio of projects with a number of contributors and how long they last and what their bug rates are.
If you go to IEEE 2018, Software Engineering in Practice, you'll find 3 papers from my group that were able to compare 800 open source projects to 150 IBM projects, because we had special access for a few months. But it's certainly very hard to do on scale.
Yeah.
Where's your accent from?
Oh, it's not New Zealand, put it that way.
Oh, yeah. Oh, yeah, mate. Oh, yeah, sure.
All right.
Oh, hang on. Are you saying I'm a Kiwi? Just a moment there.
We'll follow up. All right. I think back
I've been insulted. Like,
We have a comment in here that says Texas accent.
Texas.
The real South. Anyway, well, with that, I'm going to say we are at the end of our hour, unfortunately. But Tim, I do want to thank you very much for this entertaining.
And please thank Ken.
Yes, and Ken, way over there. Hello, thank you. And he's been good at keeping you on task, I know, as well. So thank you for making this possible.